We've studied the mass spring system, and at its most general, it's a driven system. It's a second-order non-homogeneous problem. Now, we've already discussed that by linearity, you can break this problem up into a homogeneous problem with non-homogeneous initial conditions. Solving that is what we'll call the homogeneous part of the solution. And it always ends up being part of this formula in terms of the fundamental set. Now, you can also then, by linearity, solve a particular problem where you've got just the driving side on the right-hand side with rest initial conditions. And that solution, the response of that, is called the particular solution. And remember, we've represented it in terms of a Green's function. What we're going to do now is try to apply the Laplace transform to this mass spring dE and see what we can learn, what kind of insight we can get, and see if it makes our life easier when we try to come to these final results. So when we apply it, remember that the Laplace transform works really nicely with initial conditions like this. So all you need to do is apply it to the differential equation. There's no special process that needs to happen. We're going to assume that everything here is of exponential order and all the transforms exist. So when we do that, we're going to treat each term one by one. So we'll assume that capital Y of S is the Laplace transform of the function we're looking for. Remember that the initial conditions are automatically included when you take a transform of a derivative. So if we just go through and we write all of this out in its most general form, we'll end up with something that looks like this, and we'll assume that capital F of S is the Laplace transform of the right-hand side. Now, from above, this will be A, this will be A, and this will be B. So if we group together everything that has a capital Y, we'll end up with something like this. We'll have ms squared cs plus k times capital Y. Now you can see that this polynomial mimics the structure of the right-hand side of the differential equation. It's a second order dE, and then we see a second degree polynomial here. Very similar to the characteristic equation we've dealt with before. There are some additional terms. We'll have ms times a minus mb minus c times a. And all of that's going to be equal to f of s. So if we group things together, we can isolate this equation for capital Y. And here's what we'll get. We'll have all of these terms that contain the initial conditions. All of those terms will be present there. And they'll be divided by that ms squared term. And I'm going to write it deliberately like this. ms squared plus cs plus k. And then we'll have, sorry, I forgot this one term over here. My mistake. So everything to do with the initial conditions is going to exist here. So we'll have our m times sa plus b plus ca. All of that stuff is going to be essentially divided by that term, and then we'll have the portion due to the right-hand side, and it also gets this term here. Now you'll see that that term appears twice, and in fact it appears everywhere. So what we're going to do is give this a new name. We are going to call this thing h of s, and h of s is essentially the polynomial that represents the structure of the left-hand side under the action of a Laplace transform. We're going to call this the transfer function. So the transfer function is actually very important. It's going to hold all the information about the left-hand side of the dE. So another way to write this expression is that we'll have capital Y of s. I'm going to call this portion here capital I because it has to do with the initial conditions. So we'll have I of s times h of s plus f of s times h of s. This is due to the initial conditions. This is due to the right-hand side or the forcing. And when you apply the Laplace transform to this dE, you can see that everything gets split up very nicely, very naturally. There's some influence due to the transfer function in each of these terms, but it all separates very nicely. Now you can compare this. Remember that when we solve a DE, there's a homogeneous part and a particular part. If we were to take the Laplace transform of both sides of these, by linearity, what we would find is we'd have this thing equals the Laplace transform of the homogeneous term, Laplace transform of the particular term. So it's very easy to see that capital Y of S is there. Because this term has an f of s, it has to do with the right-hand side. So you can see that this is the Laplace transform of the particular solution, whereas this term has the initial conditions, so it's related to the Laplace transform of the homogeneous solution. Now the transfer function is convenient, very convenient for us. So the transfer function allows us to easily swap right-hand sides. So for example, if I say, oh, my driving function is a 1, its Laplace transform is 1 over s, and that means that the Laplace transform of the particular solution, the right-hand side, is just the transfer function over s. If I take f of t is equal to the sine of omega t, as we've done before, right? The transform of this is going to be omega over sine s squared plus omega squared. And that means that the Laplace transform of the particular solution is just going to be h of s omega s squared plus omega squared. It becomes very, very easy for me to swap out the right-hand side and figure out how to get the Laplace transform of the right-hand side. But we are not starting with right-hand sides, right? What we're trying to do here is solve the problem in time space, in time domain. So there's a natural question here. How do we get back y of p? And the point here is that if I've been telling you that y of p, or the Laplace transform of the particular solution, is just the transfer function times the transform of the right-hand side, that would mean that the particular solution should just be the inverse of this product. Now, unfortunately, we don't know what that is. We really, at this point, don't have any idea what the inverse of a product is. And it turns out that this is going to be very important, and we're going to study this right now, but I'm going to try to motivate this to you with an example. And unlocking this secret is going to tell us so much more about a topic we've revisited earlier. So we're going to study this with a first-order constant coefficient, dE, because we already know what to do with these. We'll have y prime minus ay is f of t. Y of 0, we'll just take rest initial conditions. Okay? So we're going to do two things. We're going to use integrating factor, and we're going to use Laplace transform. And what we're going to try to do is gain some insight as to what the answer to this question is. Because if I've got two different ways of solving the same problem, it's going to tell me how to get there. Now, I know already that if I were to use the Laplace transform on this, it would become very straightforward. I would take the Laplace transform of both sides. The first term, I could use linearity. This term is going to go to 0. Minus ay of s would be capital F of s. Now, no secret here, we'll have s minus a y of s is f of s. And so that means y of s is just going to be 1 over s minus a times f of s. So in this simple first order situation, this thing right here is the transfer function. This expression here holds all the information about the left-hand side. Now remember, the particular solution, or y of t in this case, is going to have to be the inversion of this thing. Now, until I know what that expression is, I can't really go any further. So this is how we are going to leave that situation off with the Laplace transform. And now we're going to go back to integrating factor. And this is something I've done several times in the course already. I've taken that integrating factor method and used it to try to motivate what we are going to do next. Now, the integrating factor is related to the term that you see there. Now, the integrating factor is just going to be e to the antiderivative of this term. So we'll have e to the minus at. The point of the integrating factor is if we were to take it, multiply both sides by this expression, the integrating factor is the magic term that will change this into a perfect derivative. The perfect derivative will have the function times the integrating factor. Now the right-hand side will just appear as is. We can anti-differentiate. Now here's where we want to take use of the initial condition that we've been given. We could do a general antiderivative and apply the initial conditions there, or we can take an antiderivative that starts with our initial value. So that's what I'm going to do. I'm going to say, let's take the antiderivative here that applies from our initial value, and what we'll end up getting is the following: 0 to t e to the minus at f of t dt. Now here's where we're being sloppy. If we do this approach here, where temptation is to use t, but we can't do it because of our integration limit. So instead of using a t, we're going to get rid of all those t's and replace it with a dummy variable. Now the dummy variable we've been using is an s. Now we've used this s in the past, and that's fine, but it doesn't matter what we choose. Now it's customary in these Laplace transform situations to use a different letter. Instead of using an s, we are going to use a different letter. It'll be called tau. So it's another Greek letter. So it'll be f of tau d tau. But remember, it's just a dummy variable. If you'd like to use the s, you certainly can. Now, that integration from 0 to t automatically takes care of the initial constant that we've got. What this is going to do is let us rewrite the expression as follows. We'll have an integral, an e to the positive at multiplied with our antiderivative, e to the a tau, f of tau d tau. For the moment, I'll just write it as an s, f of s ds. And remember, but because this is an antiderivative with respect to s, I can pull this expression inside. So I'll have y of t, 0 to t, e, and now what I'll find is that I can rewrite this thing as e to the power of t minus s, and then I'll have an f of s ds. Now you might be saying, I'm not really sure what's happening. What's going on here? Okay, so now's the time to compare what we've done. According to the Laplace transform method, the solution to this problem was the inverse Laplace transform of 1 over s minus a times this f of s. According to the integrating factor method, the solution to this problem is just given above. 0 to t e to the minus, or e to the at minus s, f of s ds. Now the reason again that we pick s, we don't pick s and we pick tau is because we don't want to confuse it with the s that comes from Laplace transform. So what we're going to do is write this as a tau, tau, and a tau. And what we want to do is compare these two things. What similarities do we see? How are these two things related? How does it relate to inverse Laplace transforms of our transfer function and of this thing? And so here's where we stop and we think about it. And we say, okay, we know that the inverse Laplace transform of 1 over s minus a would just be e to the power of at. Now you can see that something's happened up there. That inverse, that e to the at appears there. And what we have to do is realize that that e to the at is kind of appearing there, but in a weird, really mixed up, strange sort of way. So it appears above in a mixed up way. You might say, well, what do you mean by this mixed up way? Right? What exactly is happening here? Well, this thing, it seems like we have the inverse Laplace transform of that 1 over s minus a, but the t has been shifted to t minus tau. And seems like we have that thing inside of an integral multiplied with this f of t, or f of tau. So the question way back when was, what is the inverse Laplace transform of a product? And unfortunately, it isn't just straightforward. It turns out that it's going to be given by some weird mixed up integral. Now that integral does contain Laplace transforms of some of the terms, but in a weird, non-obvious way. And so now what we're going to do is, to make sense of this, we are going to define something called a convolution. And the convolution is essentially us trying to unpack that weird integral that we get. So if I were to take the convolution of two functions, we're going to put this little star notation here. We are going to define it as an integral like this. The first function will have an f of tau. The second one will be shifted, t minus tau, d tau. And this is a function of t, so the t appears in these specific spots. So that's exactly the kind of thing that I'm seeing up there. You'll notice that this thing up here is in fact a convolution. So it's because of this integral here that I'm saying, oh, I should define this special thing. This special thing is called a convolution. It's a weird way of jumbling up all the functions. So we can see that the inverse Laplace transform of this 1 over s minus a, f of s, is really the convolution of this function's inverse Laplace transform with this one. So it would be the inverse Laplace transform of 1 over s minus a convolution with f of s. You might say, well, why? Okay, well, the result that I got above says it has to be formed in this strange integral. Okay, so it's going to be 0 to t f of tau e to the a t minus tau d tau. Now I used a special property here, and I'm cheating a little bit. Now here are some properties of convolution. It will turn out, as I've just shown you, the order of convolution doesn't matter. Now I'm not going to state or approve these, but they're kind of boring and you might be able to believe them. They're all nice. Constants can be taken out of convolutions or put back in beside different terms. And the order in which you do convolutions doesn't really matter as long as you stay in the same spot left to right. And you can see that I swapped the order of those two to get them into here. And this is a really important idea. So this is something called the convolution theorem. If you have the Laplace transform of a convolution, it will turn out simply to be the product of Laplace transforms. This is the weirdness of Laplace transforms. In frequency space, products are nice, but they're not nice in time domain, right? In time domain, they turn out to be convolutions. And that's the nice thing that kind of saves us here. So if we say, I want the inverse Laplace transform of a convolution, of a product, then the inverse Laplace transform of a product turns out to be a convolution. So in this problem here, where we started with this rest initial condition, we found that the solution, according to good old integrating factor methods, was given by this. And we found that according to Laplace transform methods, this thing right here is the inverse Laplace transform of 1 over s minus a, but it's just been shifted to t minus tau. And this thing was the inverse Laplace transform of f of s. So the convolution is an amazingly important property that allows us to extend what we know about particular solutions. And we'll talk about this in the next video.